Hello, class. Okay, so we're going to talk about error analysis, which is something, we're going to do our first lab next week. And that's a very important part of any experiment. Usually in an experiment, we're testing a theory or, trying to measure something. And so we need to know, if we're testing a theory, it's like the theory predicts a certain result. If we do the experiment, are we going to get that exact result predicted by the theory? No, we're not, because there's errors involved in every measurement. And so when it comes to testing a theory, the question kind of becomes, is the result that we got significant enough that it can't be attributed to the errors that we expect from this kind of experiment? And that's really a statistical question in nature, because we never know exactly what errors are. If we knew exactly what an error in a measurement was, then we wouldn't really have an error in the measurement. We could just correct for it. If I measure something and I said, well, I measured 11 centimeters, but I know it was actually exactly 1 centimeter off, well, then it's 12 centimeters, or 10, depending on which way the error goes. So, errors are kind of unknown, just fundamentally. They have to be by their nature. But what we can do is estimate them. And so, the question is statistical in nature, which is not something that we can get into too much in this class. And also another problem with this class is estimating errors very often requires calculus, which is also something that we cannot do. So we're going to keep this very basic. All right, and then when it comes to measuring, testing theories, that's one purpose of doing an experiment. Another is just trying to measure something. Like, let's say we want to measure g, little g. So measure the acceleration due to gravity. And we could easily design a simple experiment. Just drop something and measure how long it takes for it to fall. So let's say we were going to do this very simple experiment here. Like, I'll drop this from the top of this board and then use a stopwatch and time how long it takes to fall. And if I drop it from rest, we know that the distance fallen is 1/2 gt squared. If we're just going to do the simplest experiment we could, see if so g would be 2d over, this would not be a very good experiment. Because what we do is we measure the height that we're dropping it from, or the distance it's going to fall, and we measure the time with a stopwatch. And again, this is just one single measurement. And that's generally not good if you can avoid it. So maybe a better experiment would be to drop it several times and get more data. But let's just keep it real simple for now. So we could measure g using this method. We would not expect to get exactly 9.8 meters per second squared. And so ideally what we would like would be g equals our measured value plus or minus something, like some error. So an example of that could be, g equals 9.6 plus or minus 0.3 meters per second squared. Something like that would be good. So when it comes to measuring things, we want to be able to estimate the size of the uncertainty in our measurement. Okay. So, again, we're not going to actually do things like that, estimate the size of the uncertainty, because that requires calculus most of the time. So, but it's important to know that that is one of the goals of doing an experiment, because we can say a little bit about that uncertainty. So anyways, let's use this kind of very simple example of an experiment to discuss. Main thing we want to do is discuss the errors involved and also classify them. There's two main classifications of errors. So we can ask the question, why, if we did this experiment, if I drop this object and just use a stopwatch to time how long it's going to take to fall, why won't we get the exact right answer? And the first thing we want to look at is, what are we actually measuring here? So we're measuring D. It looks like we're measuring D and the time as well, and there will be errors associated with those measurements. So there will be a measurement in D and a measurement in time. Actually, I would argue there's kind of two errors when it comes to measuring time, because we have to start the stopwatch, and when it, like right when we drop it, we have to hit start, and then when it hits the ground, we have to hit stop. So let's call this T start and T end. Now you could kind of say the same thing for D. Say we use a meter stick to measure the height of this that we're dropping it from. There's actually two measurements, like where you start and where you end. But in this case, let's just say measuring the distance. We can just set this on the ground, so maybe there won't be a significant error on that end. We could have a little bit here. Okay. Now, let's just look at one of these measurements. Let's start with D itself. Why is D going to be inaccurate? So we're using a measure. I'm going to actually do this. I'm going to set the meter stick down here. And what I'm getting is around 91.6 centimeters. So there is definitely an error associated with that measurement, or more accurately, there are several errors associated with this measurement. So we could make a list of them, but just even something simple like measuring something with a meter stick. First off, this is not really a meter. Remember, the standard meter is defined as a distance that light travels in a very tiny fraction of a second. We're not using that. We're using a meter stick, which, they claim it's a meter. But, let's just say meter stick could be a little off. Meter stick calibrate. That's it. So, the meter stick itself could be not calibrated perfectly. I'll just say meter stick off because I'm running out of room to write. Okay, so that's one error. Another error, if I look on the meter stick, there's nothing that says 91.6. I guess I can hold this up. This is a very old and faded meter stick. But, it goes like 90, 90, 91, and then you can see those tick marks between 91 and 92. And again, the edge of the height of the board, that's not going to fall exactly on those tick marks. So let's call that an interpolation error. We have to, we're reading something just visually, and the number we get isn't usually going to be exactly something that's on our device. We have to kind of look. It was closest to 0.6. So there will be a little bit of an error, but maybe more significantly, that limits how precise we can ever get with this meter stick. I could say it's closer to like 0.6 than 0.5 or 0.7, but there's fundamental limits to what you can do with a meter stick. So this interpolation error. Another error. I just did this. I'm going to exaggerate this because it could be a factor, but it'll be easier to see. Like when we talk about the height of this board, we measure it from like the bottom of the board to the top of the board, but we want to measure it so that the meter stick is perpendicular, like to the floor, or to the top and bottom planes. So like if I were to measure it like this, it's hard to see the numbers now, but now I could say this is about 94.5 centimeters because the meter stick is at an angle. And so maybe improper. Yeah, the thing is we want to be pretty specific when we're talking about errors. So I don't want to say improper measurement. I want to say angle of meter stick. That's pretty precise. One thing that's very tempting, students do this all the time, is use the term human error, which you should not use that term. You want to be precise. And maybe it wasn't even precise here when I said the meter stick could have been off. There could be just fundamental issues with how it was calibrated. I mean, obviously they're not going to do it perfectly. They'll probably do it good enough. Another possible factor, though, is it could depend on the temperature. Things expand when they're heated. These are kind of small factors, and it would only matter if we're going to be doing something, very precise. But there could be like multiple reasons that the meter stick could be off. And again, maybe it could depend on, from one day to the next, depending on the temperature. Yeah, and then the angle of the meter stick, maybe you want to be more clear what that means, but just like not measuring the perpendicular distance. Now, another possible distance is just the, say, definition of height. Now, I have to be clear, I'm just listing these. But what we mean by that, and again, this is a very, very minor issue in this particular measurement, but it's kind of a limiting factor when it comes to how precisely we can define things. Because I'm saying I want to measure like the height of this board. But is the height consistent? Like what if we start at one end and measure the height? Is this like a perfectly flat line? And no, I mean, it could have a slight angle to it. That could be another factor, like in a lab, if you're measuring the height of a table, like the legs are adjustable, maybe it's not perfectly level, and so if you measure the height at one end, maybe it's going to be a little bit different than at the other end. So, that's called a problem of definition, and even if you want to get really precise, it doesn't even, like, if you look at the surface under a microscope, it looks very flat top. It seems very smooth, but if you were to zoom in with a microscope, it would be a little more jagged. So, like the height could vary, as you move along along the board. Okay, so the thing is, if we wanted to, we could probably, continue and just keep on listing more and more reasons that the simple measurement of height is off. But we really don't want to do that. One thing we'll learn, you could have a huge list of errors for any experiment. But then when you do the numerical work and try to figure out, like, we did this example, ultimately we're going to find G. Let's say, I think I used this example. So it's kind of a standard form that you would write things in science. And, when you come up with this number, you look at all the errors, and they each contribute something to this number. And what's interesting, though, in real experimental work, you'll find that you can have an enormous list of errors, But let's just say one of these errors, like say time is going to be a huge factor in this experiment, mainly because this is a very crude experiment that was not designed very well at all. Actually, we wouldn't get results nearly this good. What we would want, even though the idea might be sound to measure G this way, what we'd want is have it so that the stopwatch would start and stop itself automatically. You know, we have a device that could do this in the lab called a photo gate, where you can drop something and it knows when it passes through the gate, and you could use that to like start a clock and then have it pass through another gate and stop the clock and measure the distance between those two gates. So something like that would be very, that would make this experiment much more precise. But, yeah, so this is a very bad experiment, so we wouldn't have an error this small doing just dropping this and using a stopwatch. But let's just say that measuring the time is the most significant error. And let's say that give us an error of that could very well be almost the entire thing, 0.3 meters per second squared. And again, remember, this is not precise just by its nature because errors are not known precisely. They're estimates. And so if you have one error, let's just call it error 1, is 0.3 meters per second squared, and error 2 is 0.001 meter per second squared, do you actually care about this one? No, it has no effect on the overall number you're going to put down at the end, because this, this is not precise. We usually do not have more than one significant figure in, the error. I have seen 2. There are some measurements that are extremely precise, where they'll have 2 significant figures for the error, but usually just 1, and so this one is just completely insignificant. So that's another very important job in error analysis, is trying to determine which errors are significant. It's usually dominated by a relatively small number of factors. So just looking at this, the meter stick being calibrated properly, I don't know if we'd even need to worry about that one. Angle of the meter stick, we'd have to be careful to do it right, but that could maybe be a little bit of a factor in this experiment. I could see that being off by we said 0.6 centimeters. Maybe that could give a small error, so maybe we'd want to take that into account. Definition of the height, I don't think we have to worry about that. And again, these are just errors in height. So just measuring the height of this object. And we could come up with a similar list for time. Like we're using a stopwatch, and you hit by far the biggest error in using a stopwatch is just your reaction time. You have to hit start and hit stop. You have to, when you drop the object, or when you see something happens, you hit start. And then when you see the next thing happen, you hit stop. And again, there can be very significant errors in both starting and stopping. And so again, but there's also the question, a stopwatch, that is not that's not an atomic clock that's based on the actual definition of a second. So, you could at least raise the question, is the stopwatch accurate? And I would say, unless there's something seriously wrong with this, like you got a defective stopwatch, the answer is definitely yes. If you're going to rely on starting and stopping something just on your own, it wouldn't take a very precise stop. The cheapest stopwatch you can buy will definitely be good enough to where the error in calibration is completely insignificant. So you want to think a little bit about just what are the significant errors. And what we're talking about here are purely measurement errors, like measuring the height of the board. And then I didn't write it down, but stopwatch, basically just reaction time and starting and stopping. So here, let's do that, stopwatch. And say reaction time And calibration, I'll write it down, and then I'll cross it out because it's totally insignificant. But, I mean, if you're going to do an extremely precise experiment, yeah, you might want to think about how your measuring device is calibrated. So these are just measurement errors. And again, these are kind of obvious that there are things that you want to look at, because in this experiment, to find g, we need the height that the object is going to fall and the time it's going to take to do so. And so it's obvious that there's going to be errors in both of those. But you don't want to just say, like, error in measuring height. You want to explain, in a little more detail, like, what errors are we talking about? And, but there's other errors than simply measurement errors. One of them is this equation actually correct? Like, will this accurately measure g for the experiment we're doing? And the answer is no. The reason, neglecting error resistance. I'll just say other errors. So we're neglecting error resistance. And so that's another error that isn't obvious from just looking at the equation. But that's something we often do in our labs. And if you want to, like, they do use this kind of method for measuring g, the acceleration due to gravity. But what they do is, I read one experiment where they had an object falling. They put it in a, like, vacuum chamber and dropped it. So, or they had it in a container, and that container was put in a vacuum chamber. So, yeah, I mean, they definitely want to take air resistance into account if you want to measure g accurately. So, yeah, so we completely neglected that. That's another source of error. Probably not that significant in this one, but maybe enough to at least mention. And again, in labs, just a little hint for your lab reports, you can very often just say neglecting friction is a source of error. Okay, so just kind of a huge topic, just figuring out errors and trying to get a handle of the size of them. But another thing we want to do is classify errors. And this is actually a very important topic. But first, I'll just mention we classify errors as either random or systematic. Okay, so a random error. Kind of a classic example here is reaction time. So, like in this experiment, we measure a time using a stopwatch. And, like say you're just looking at when it hits the ground, you want to hit stop. Now, of course, you're kind of going to anticipate that there will be a little bit of a delay from when you see it hit the ground and when you hit the stop button. Now, I guess if you really wanted to, be obsessive about listing these errors, is you could, at least in theory, it's true that, when you see it hit the ground, that's not when it actually hit the ground. There's a little bit of delay because the light had to actually reach you. Now, that delay would be completely insignificant, and so it wouldn't show up numerically, so we don't want to mention that, but, yeah. But anyways, you're probably going to know that, like, once you register in your mind that something happened, there's going to be a little delay between when you decide to push the button and when you actually push it. So, when it comes to, timing this, you're going to try to kind of maybe hit the button a little early to compensate for that. And so that's kind of the fundamental feature of a random error, is that it could either be too high or too low. So that's a fundamental issue of random errors. Or say you're measuring the height. Maybe I said it's 91.6, maybe it was actually closer to 91.7, so I underestimated the error. Or if I came back the next day, maybe I would have said 91.8 and overestimated it. So again, those would be random errors, just trying to figure out like that closest thing you can identify on the instrument. You know, maybe you go too high, maybe you go too low. So those are random errors. Systematic errors, so these, I don't want to write this here, but systematic errors, these are always in one direction. They always push the result in one direction. So like, let's look at an example of a systematic error, and that is neglecting air resistance. Because air resistance is always going to slow the object down. So like our time, it's always going to take longer to fall if air exists than it would fall in a vacuum. And so, yeah, like air resistance, that's always going to throw off our measurement in one direction. Like the meter stick not being calibrated properly, or the stopwatch not being calibrated properly, those are systematic errors. Like if the meter stick, if this was, say, actually 101 centimeters, that's always going to throw off every measurement in the same direction. It's either going to cause us to overestimate or underestimate every measurement we use with this device. So which one is it going to be? Let's say this was actually 101 centimeters. So if I measured something that was 101 centimeters, I would read it as 1 meter. So if this was calibrated to be 101 centimeters, then that would cause me to underestimate, underestimate every measurement made with this device. And so that's a fundamental difference between random and systematic errors. Random errors you can overestimate or underestimate. Systematic errors always throw off the results in the one direction. Now, why do we care? And the reason is we want to deal with these types of errors differently. Like random errors, if you have something that's truly random, like half the time it's going to go, too high, half the time too low, and kind of like the same amount in either direction, if these results are purely random, you can eliminate random errors by taking repeated measurements. So if we repeat this experiment, if we do this experiment once, there will be some random errors that contribute. I'll write this down again. All right, I think I wrote down 9.6 plus or minus 0.3. So again, if we do this experiment once, there is a random error, and there's nothing we can do about that. It's there. But if I repeat this experiment like 50 times, we can pretty much eliminate that random error. We can make it so small, by doing enough trials, we can make it so small that we can just disregard it entirely. Just like taking an average. Some values are too high, some values are too low. When you take the average, they're going to cancel each other out if you do enough of them. Now, there's always limitations to this, though. First off, the errors have to be truly random. Like I would suspect using a stopwatch, the errors are not purely random because maybe you have a tendency to overestimate rather than underestimate. And if you repeat it 100 times, you're going to continue to do that. You might tend to do one more than the other. So repeating measurements is great to eliminate random errors, but there are limitations. And another issue is, you have to be able to actually repeat the experiment without changing it. Like if I were to do this experiment multiple times, like right now I'm just holding this up. Maybe I'm holding it up too high or too low. That itself is a random error. But if there's any details are off between one trial and the next, that limits your ability. You're not really measuring the same thing, so that introduces another error. But generally, if random errors are significant, you want to repeat the experiment many times, or get more data involving these random errors, so you get a lot of cancellation. Now, systematic errors, the only way to deal with them is to be aware of them. And that's really the tricky thing. Systematic errors, there is a very large number of systematic errors that can exist, and they're very easy to overlook. And so, like if you're going to be an experimental scientist, you have to be very careful in dealing with systematic errors. The only way you can really deal with them is just to be aware of them, and then try to get an idea of how big they are. Like, say you expect your measurement, like the systematic error, to overestimate by like 1 millimeter. If it was a measurement of distance, if you know that systematic error exists and it's like has a magnitude of 1 millimeter, then you can just subtract 1 millimeter for the result and say we took care of that error. You can only do that with systematic errors that push things in one direction. It doesn't make any sense for random errors. But you have to both know of them, the existence of the systematic errors, and also have an idea of how big they are so you can correct for them. And so that's a really tricky thing in experimental science, just knowing all the systematic errors. Okay. I put a picture in the notes that I want to talk about, and then we'll kind of stop there when it comes to error analysis. Kind of a nice picture about, there's two terms that are very useful, called accuracy and precision. And, these might sound like the same thing, but they have very different meanings. And I think my favorite example of this is the Hubble Space Telescope, which, I remember when they launched that thing, and it was very disappointing at first, because it gave very fuzzy pictures. There was a serious mistake in making one of the elements. I think it was like one of the mirrors. There was a very serious mistake that just made the telescope almost worthless. And so they had to send astronauts up there and put a corrective lens, and then it worked great. And so you might think, well, whoever built that mirror did a bad job. But no, actually they did an exceptionally well job of designing the wrong mirror. So there was a miscommunication about the exact specifications of this mirror, and so they were designing the wrong mirror, but they did a really good job of it. And so it's kind of the difference between accuracy and precision. So like I stole this picture from a book. It was a book called Introduction to Error Analysis, which is a really good book. If you're going to like science or engineering, definitely recommend reading it. But you have like a bullseye. So like here's the bullseye. This is what you're aiming for. And again, this is just not to be taken too literally. Like measuring g. This is the acceleration due to gravity, the bullseye. And if you do a good measurement, you're very close to it. And so an accurate result would be to hit the bullseye. Like here, this is an example of an accurate result. Well, let's say we take several data points and they look like this. Now, we would say that this experiment had good accuracy, but not very good precision. And just to be clear what I'm talking about here, let's look at another example. Where say your data looks like this. Now this has very good accuracy and very good precision. So precision means like you're measuring, same thing over and over again. And like here, your results are kind of scattered around. But here, this is very precise and also accurate because like here, if you like average these, it's pretty close to the bullseye. Here, if you average them, it's also close. So this is good accuracy and precision. Now, actually, I'm going to erase this. I'll draw another picture. This is kind of like the Hubble picture here. Where this one would be very precise, but not at all accurate, because you're trying to measure something here, but like all your measurements are off over here. So this is precise, but not accurate, because you're not anywhere near the bullseye. This would be a case where you have like a systematic error. And I'm looking at the screen, it's hard to, okay. So, yeah, accuracy and precision. Now, if you just look at your data, it might look like you can look and say, okay, well, this is still pretty good, because if you have a lot of data points, this is kind of also illustrates why, here we have some random errors that are making these results kind of scatter around. And so if you just did one measurement, maybe this would be your data point, your result would not be accurate at all. But if you take all these data points and kind of take the average, that could be a good experiment, even though your individual measurements are not accurate. So these random errors can be reduced by repeating the experiment. Now say you've done an experiment. Can you just look at your results and say, yeah, I did a great job? Not necessarily. What I'm going to do, let's compare these two pictures here. Like say we're measuring G in this class, and in this, let's say we get G equals 9.8 plus or minus 0.1 meter per second squared. We can say we did a great job. Here's our results. Very precise, so a very small error, and very accurate because we got the right value. Where over here, maybe we'll say G equals 10.5 plus or minus 0.1 meter per second squared. And we can clearly say, well, we know G is 9.8. And so we screwed something up. But what if, very often the purpose of an experiment is to measure something. And so a more accurate picture might look like this. So like this target is the bullseye, but if you're measuring something that's unknown, you have no idea where that bullseye is. And so if you just look at these results, they both look equally good here. And so this is why it's so important to be aware of systematic errors and being able to correct for them. Because if you're doing like an original experiment or measuring something that is unknown, you have no way of knowing where the target actually is. And so if you get very precise results, you might think you get a good job, but maybe it was totally off for some reason that you didn't see. Again, we're not going to be doing anything like that here. We're measure things that are unknown. And again, it's kind of a self-correcting issue overall, because in science, you don't just measure something and say, okay, we did that, we move on. Ideally, you would measure the same thing using different methods. And so, like, say two people do experiments, and one got this result where this was right on the, there's no bullseye, but, say that we'll just put some arbitrary point let's just say we have let's just say some person gets their random or their results. Here someone else gets their results, and the average value is here. And they both have this. The error bar is kind of like this. Clearly something is wrong. We don't know which of these is wrong, and so then at least we know we've got to re-examine these experiments and look for systematic errors. Because, they should kind of overlap. If all our data points are in this circle, and this experiment has all their data points in this circle, and they're totally separated, something has gone wrong. And this is always happening in physics, where you measure things in different ways. Because the type of systematic errors that are going to exist are kind of particular to whatever experiment you're doing. So if you measure the same thing in a different way, you'll have different systematic errors, and maybe one of them has one that's overlooked and the other doesn't. And so, yeah, you can then go and kind of re-examine both experiments and figure out what went wrong. So yeah, you never just do an experiment, say, okay, we've done this, and move on. We always want to double check these things. And yeah. Okay, so just a really quick summary of what we want to do in this class. We can't do calculus or statistics, so we're really not going to get into the numerical work of error analysis. But it's really important to understand concepts like random errors, systematic errors, and like this kind of picture the difference between accuracy and precision. And another important thing to take away from this is your job in doing error analysis is not just to make a list and say, here's all the errors. In measuring the stopwatch, we didn't take into account the speed of light, that time delay that it took that light had to travel that meter. Because there's no way you're going to be doing an experiment precise enough where that could possibly be a factor. So you want to be able to identify kind of the significance of the errors as well. And yeah, that's all we're going to do in this class.